In this example, a block of elastic solid is being compressed by normal stress sigma x. And now notice it has two containing walls, such that there could be no deformation in that y direction. Now, with this in mind, what we want to do is find the values for k for essentially plane strain and plane stress conditions. Now, we're given this relation such that sigma x is equal to k times epsilon x, and we're also given that the Young's modulus is 70 gigapascals and the Poisson ratio is 0.3. So we can start off with the plane strain condition. So in plane strain, epsilon sub z is going to be equal to gamma sub yz, which is going to be equal to gamma sub xz, and that's going to be equal to 0. But now also, since we said we have no deformation in that y direction because of the essentially the wall boundary, we can also say that epsilon sub y is going to be equal to 0. Now the next step is we'll essentially use Hooke's law to relate our strains to our stresses. So once we find our stresses, then we can essentially find what this k value is and then calculate its actual value. So I just pre-wrote this out just to save some time, and I defined our four strains to be equal to 0. So now we can calculate for the 6 different stress values to essentially form our essentially stress field. So now, sigma x, after doing matrix multiplication, is going to be equal to epsilon x times lambda plus 2g. And then sigma y is going to be equal to sigma z in this case, and that's going to be equal to epsilon x times lambda. And then tau xy is going to be equal to the shear modulus g times gamma xy. And then tau yz is going to be equal to tau xz, and that's going to be equal to 0. So right here, I should probably define that lambda above is equal to the Poisson ratio nu times the Young's modulus E, and that's divided by 1 plus nu times 1 minus 2 nu. And then G, the shear modulus, is going to be equal to Young's modulus E divided by 2 times 1 plus the Poisson ratio, nu. So, by this relation, we essentially want to find what this k value is. So we can use this equation right here, such that k is going to be equal to lambda plus 2 times g. So we can make the substitution for our equations, and let me move this off to the side so we have some more room, and then let's make that blue, just for fun. So then we can start to plug in our values. So we'll have 0.3 times 70 divided by 1.3 times 0.4. So we're essentially just substituting these two equations, and then we're substituting the values for Young's modulus as well as the Poisson ratio. And then let me add a bracket here for units, because these will be in gigapascals. And then we'll have 2 times 70 divided by 2 times 1.3. So we get a final k value equal to 94.23 gigapascals. And that is the first part. So now, the next thing that we need to do is solve for the plane stress condition. So now in plane stress, we have that sigma z is equal to tau yz, which is equal to tau xz, equal to 0. And now, similar from before, so we can't have any deformation in that y direction, so we're going to have that epsilon sub y is equal to 0. And then we'll pretty much set up Hooke's law again, except this time, notice that the matrix is slightly different. It's essentially sort of inverted, so that we can then convert from our stresses to our strains. So now we can essentially multiply across and then solve for the strain values. So we'll get that epsilon x is equal to 1 divided by E times sigma x minus nu times sigma y. Get epsilon y is equal to 0, which is equal to 1 divided by E times negative nu sigma x plus sigma y. So we can say that sigma y is equal to nu times sigma x. That'll be important for later. We also get that epsilon z is equal to negative nu divided by e times sigma x plus sigma y, and then gamma xy is equal to 2 times 1 plus nu divided by e times tau xy, and then we get that gamma yz is equal to gamma zx, which is equal to 0. So now, the reason we tried to make a relation between sigma y and sigma x is so we can then plug it into this first equation up here, such that we get epsilon x is equal to 1 divided by e times sigma x minus nu squared sigma x, because then we can write that sigma x is equal to e divided by 1 minus nu squared times epsilon x. So now you can see where this is going. So then we can say that k is equal to e divided by 1 minus nu squared. And then we can just plug in our values. We have 70 gigapascals minus, divided by 1 minus 0.3 squared. So then we get a final k value equal to 76.92 giga. Oh, gotta erase that. We get gigapascals.